Today, we're cutting through the noise around artificial intelligence. You hear about it every day in the news, finance, medicine. But what are the actual, the foundational ideas that are powering this whole thing?
It is a massive field, and it stretches from, the deepest roots of philosophy and logic all the way through to some very practical real-time engineering. The sources we've drawn from today, it's a whole stack of academic texts. They show that AI is really everything. Perception, reasoning, learning, action, the whole package.
So our mission is to give you a kind of deep dive shortcut. We want to unpack the fundamental concepts, track the history a bit.
Yeah, see what shaped the field.
Exactly. Highlight the surprising modern achievements, and then, ground those future risks in reality. We're not here to just read a textbook.
No, we're here to pull out the core insights.
So let's start at the very beginning. If the goal is building intelligence, what is the core mission for an AI researcher?
Well, the core mission isn't just about mimicking human thought, though that was certainly part of the history. Fundamentally, it's about understanding and, crucially, building intelligent entities. And in AI research, that whole pursuit really zeroes in on this idea of the rational agent.
Okay, let's unpack that. The concept of intelligence. Historically, people have tried to codify what intelligent thought even means for millennia. Where did that first idea of, right thinking come from?
You have to go back thousands of years to Aristotle. He was really the first person to try and formalize what right thinking is. He set up the system of syllogisms, those irrefutable reasoning processes. That was the original attempt to define the laws of thought. If your reasoning followed his rules, you were thinking logically.
Yeah.
Correctly.
Okay, so that sets the stage for rational thought. But just thinking rationally, that doesn't mean you can act effectively in the real world. That's a huge gap to cross.
It is. A massive one. Rational thought is necessary, but it's not sufficient. You need a theory of rational action. This is the great jump from formal logic to making decisions when things are uncertain. It's precisely why the concept of the rational agent became the bedrock of modern AI. A rational agent acts to maximize its expected utility.
And utility is the concept you really need to hold on to here. Because maximizing utility is so much more complex than just, checking a box for a simple goal.
Absolutely. Utility is what lets an agent handle the complexity, the uncertainty, the conflicting goals of the real world. Think about a self-driving car. It has conflicting objectives. It wants to get you to your destination quickly, but it also has to maximize safety. If safety was the only goal, the rational agent would just keep the car parked permanently.
And if speed was the only goal, it would just drive recklessly.
Right. So the utility function specifies the trade-off. The rational, acceptable trade-off between making progress and incurring some acceptable risk. It allows for nuanced decisions where rigid goals would just lead to paralysis or disaster. It's really the mathematics of compromise.
So once we had that theory, the mid-20th century was just incredible optimism, almost reckless. The press was full of headlines about electronic superbrains. Researchers thought they were 5 years away from human-level intelligence?
Yeah, that era of intense early optimism in the 50s and 60s, we often call it GeoAI, good old-fashioned AI. It was rooted entirely in that formal Aristotelian logic. The pioneers, people like Minsky and McCarthy, they believed all intelligence could be captured with formal representation and reasoning rules.
But reality hit pretty fast and pretty hard.
Yeah.
If you're defining the world with formal logic, what was the big roadblock that just stopped everything cold?
It was a problem known as the combinatorial explosion. As soon as you tried to apply this logic to a slightly complicated problem, like a chess move or routing traffic, the number of possibilities the system had to search just grew exponentially. It became too large for even the fastest computers back then to handle.
And this wasn't just some academic problem. This had serious financial consequences. The Lighthill Report in 1973 specifically pointed to this failure, this combinatorial explosion, as the reason for the British government to pull funding from most AI research.
That report kicked off what we now call the first AI winter. It taught the field a very harsh lesson. Relying only on brute force logic and searching massive state spaces, it just wasn't a sustainable path forward.
And what's truly fascinating is how many brilliant ideas were developed then but were totally orphaned because the hardware couldn't keep up. There's a wonderful little nugget in the sources here about backpropagation. The engine of modern deep learning was actually developed way back in the early 1960s by people like Kelly and Bryson.
and it just sat on a shelf for decades. It was basically ignored because we didn't have the parallel computing. We didn't have the massive data sets to make it powerful. It had a little resurgence in the 80s, but it only really exploded in the 2010s when the hardware finally caught up with the theory. It's a perfect illustration that sometimes the big ideas have to wait for the tech to be ready.
Speaking of the tech, let's just talk about the sheer scale of computation. Our source stack compares the human brain to a modern supercomputer. A machine like the Summit supercomputer has about 1 million CPUs and GPUs, and it clocks in at roughly 10 to the 18th operations per second.
Which sounds impossibly fast. But then you look at the biological equivalent, and it's humbling. The human brain has so many more processing units, 10 to the 11 neurons, 10 to the 14 synapses. Its individual cycle time is much, much slower than a silicon chip, but the total operations per second is still in the neighborhood of 10 to the 17.
So the computer is technically faster in raw ops, but the brain is running these massive parallel computations on a scale that just dwarfs current machines.
And that's the core lesson we've learned. Future increases in AI functionality, they're expected to come from leaning into massive parallelism. We're basically taking a page from the brain's playbook. We're moving away from making a single processor faster and focusing on sheer breadth. It's this curious convergence where engineering starts to mirror biology.
So if an agent has to act rationally, it first needs a way to represent the world internally. This gets us to expressiveness. How much detail can it actually see?
The sources break this down into 3 levels, each more expressive than the last. The simplest is the atomic representation. Think of the state as just a single black box. The agent knows it's in state A, but it has no idea what makes up state A.
So what's the next step up from that simple black box?
That would be the factored representation. This is where the state is treated as a vector of attribute values, like a spreadsheet. The world is a set of attributes, temperature, location, and so on, each with a value. This is essential for things like Bayesian networks.
And then finally, the most powerful level, structured representation.
Right. This is where the agent moves beyond simple facts and starts to see the world as made up of discrete objects and, critically, their relationships. So instead of just a list of facts, the agent can express that John is the father of Richard, or the box is on the table. This power comes from first-order logic, which is so much more powerful than simple propositional logic because it can handle those objects and relationships.
But once you start dealing with objects and relationships, historically, you run smack into the frame problem. What made that so tough?
The frame problem, historically, it required the agent to explicitly state everything that did not change when an action happened. So if you moved 1 block on a table, the agent had to state that the color of the walls didn't change, the temperature didn't change, gravity didn't change, on and on. You'd end up with this impossible list of non-effects for every single action.
So how did they finally manage that mountain of information?
It was largely solved by something called successor state axioms. This was an elegant solution. Instead of defining what doesn't change, you just define the conditions under which a specific thing does change. It localizes the definition and shrinks the logic down from that impossible list to a concise rule.
Okay, so the agent can represent its world. Now it has to figure out how to act to reach its goals. That brings us to search strategies. We have the simple, uninformed methods, and then we have the smart, informed approaches.
Informed search is where the magic really happens. It uses a domain-specific hint, a heuristic function, which we call HAN. It gives an estimate of the cost to get to the goal from any given state. It's an educated guess that guides the search.
And the gold standard for using that heuristic is the A-search algorithm. The formula, Fn equals Gn plus Han, can look a bit intimidating, but the idea is actually beautiful, isn't it?
It really is. The Gn part is the actual cost you've already paid to get where you are. The HON is that educated guess of the future cost. So A works by always choosing the path that minimizes that total estimated cost, FAN. It's the ultimate pragmatist. It looks for the cheapest path so far and the most promising path ahead. And if your heuristic is good, it's guaranteed to find the absolute best solution efficiently.
A is perfect when you can hold the whole map in memory. But if the problem is too huge, you have to turn to local search. And here's a great distinction: the difference between hill climbing and simulated annealing.
Right. Imagine you're trying to find the highest point in a very foggy mountain range. Hill climbing is the greedy approach. You only ever move uphill, one step at a time. It's super fast, but if you hit a small peak, a local maximum, you stop. You think you found the highest point, but a much taller peak is hidden in the fog nearby.
So how does simulated annealing fix that fatal flaw?
Simulated annealing introduces a bit of controlled randomness. Most of the time, it acts like hill climbing. It moves uphill, but occasionally it allows itself to take a random step downhill. This lets it jump out of those local maximums and keep searching for the true global maximum. It combines the efficiency of a greedy search with the completeness of a random search. It will eventually find the highest peak.
And all of these complex mechanisms, they all serve that one core goal, maximizing expected utility, or MEU. But we have to ask, why is MEU so central? Why is it the only rational way to make decisions? Why can't I just invent my own system?
Because if you deviate from the basic axioms of probability theory, you create a situation where you are mathematically guaranteed to lose. This was shown powerfully by Definetti's theorem way back in 1931.
Tell us about that, the mechanism of failure he proved.
Definetti showed that if an agent's stated beliefs, how likely they think something is, if those beliefs violate the axioms of probability, another agent can set up a series of bets against them. This combination of bets is called a Dutch book, and if the first agent accepts these bets, they are mathematically guaranteed to lose money every single time, regardless of the outcome.
So it's not just that following probability is a good idea. It's that if you don't, your system is fundamentally incoherent. It's exploitable.
Exactly. The math forces you to be rational, or you face inevitable failure. It's why MEU is the non-negotiable definition of a rational decision maker.
And this abstract idea of utility has very real, measurable applications. We see it in the sources when they discuss healthcare, specifically the QALY.
The Quality Adjusted Life Year, or QALY. It's used in decision theory to measure the value of different health outcomes. It quantifies the value of a year of life, but weighted by the quality of that life. For example, studies show that kidney patients are often indifferent between living 2 years on dialysis and 1 year at full health. They're expressing a clear utility trade-off. They'll accept a shorter lifespan to avoid the disability and inconvenience of the treatment.
So if the early decades of AI were defined by failing to beat that combinatorial explosion, the last decade has been defined by conquering it. Thanks to better hardware, new architectures, the aha moments are now almost everyday things.
The speed of progress has been breathtaking. Consider complex strategy games like Go. The number of possible moves vastly outnumbers the atoms in the universe. It was once considered impossible for AI, yet AlphaGo soundly defeated the world champion. And beyond that, we've seen AI master complex video games like StarCraft 2 and Dota 2, which require real-time planning and handling partial information.
And the real-world applications are just as compelling. These aren't just games anymore. Look at Waymo's test vehicles. They passed 10 million miles driven on public roads and then soon after started offering a commercial robotic taxi service to the public.
Another fascinating example is in logistics. Autonomous fixed-wing drones have been used in Rwanda since 2016 to deliver blood across the country. This is a high-stakes, real-world problem being solved by AI in an environment where human pilots face huge challenges.
And crucially, the performance is getting to be on par with, or even better than, human professionals in very specific tasks. In medicine, AI systems are now achieving a diagnostic performance that is, on average, equivalent to healthcare professionals for things like metastatic cancer or ophthalmic disease.
Yes, the data is very clear on that. The LANA system, for example, achieved a stunning 99.6% accuracy on one specific diagnostic task. These modern triumphs just confirm that having access to greater machine intelligence is actively raising the ceiling on what humanity can do.
But with that increased capability comes this necessary conversation about risk and governance. If we can build more powerful tools, we need guidelines.
Absolutely. And the first high-profile risk that demands a global discussion is lethal autonomous weapons, or LAWWs. The discussion around this is already quite formalized.
How far along are those discussions?
Formal expert talks on the risks of LAWWs started at the UN back in 2014, and by 2017 they had moved into a formal pre-treaty stage. So the international community is actively grappling with this before the technology becomes fully mature and widely deployed.
Another societal challenge that comes directly from this scalable intelligence is surveillance.
Right. Pervasive oversight becomes economically feasible with AI. Using computer vision, speech recognition, AI provides a scalable way to do mass surveillance that completely bypasses the cost and tedium of manual human monitoring. This makes the question of governance paramount.
And governance is currently moving on two tracks.
Precisely. On one hand, you have voluntary self-governance principles being developed by the corporations and researchers themselves. On the other hand, governments are setting up advisory bodies to create regulations for specific use cases, trying to ensure the technology is deployed responsibly.
So this deep dive has really shown us the full arc of AI, starting with Aristotle's search for perfect logic, through the roadblocks of that combinatorial explosion, and into this modern era defined by probabilistic reasoning, utility theory, and massive parallel computation. We've seen how the tech had to mature to move from that simple atomic view of the world to one based on structured, object-based knowledge.
And if you connect that journey back to those early, heady expectations of building electronic superbrains, the key insight is still so powerful. Despite the increasing speed of our computers and they get faster every year, intelligent behavior in the real world isn't characterized by infinite brute force. It's characterized by the careful, efficient use of finite resources and, surprisingly, a measure of necessary imperfection to navigate uncertainty.
That concept, necessary imperfection, is a profound thought to leave you with. If intelligence requires tolerating a degree of imperfection to handle the chaos of the real world, how much imperfection must we, as users and citizens, tolerate in a truly rational agent, especially when we feel comfortable handing over consequential decisions? It's a challenge that takes us from the purity of ancient syllogisms right to the pragmatic reality of those autonomous drones flying blood across Rwanda today. Thank you for joining us for the deep dive. We hope you feel thoroughly informed and ready to explore that question further.